Hello everyone, welcome back. So, we are in week 3 and this is our lecture 3. So, let us continue our discussion. Today, we are going to learn principal stress. So, as of now, if you recall, we start with a 3D stress field. So, the 3D stress field is given and that is defined by 3 normal stresses along x, y and z direction, and then we have shear stresses and also this matrix is symmetric. So, this is our starting point, right. Now, if we just quickly draw the diagram. So, we have a differential 3D element over which these stresses act. And we can identify different planes over which these stress components act. Let us mark it. So, along x we have sigma xx, then tau xy, tau xz, then we have on y plane sigma yy. So, this is tau xy and tau yz, and on this plane we have sigma zz, then tau yz, tau xz. I am not drawing the components acting on the opposite faces, but from this we can easily identify the stress components that acts along x, y and z direction. Now, given this stress field, we can identify Tx, Ty, Tz acting over a plane, right. How do we do that? The plane is defined by its direction cosines. So, we have nx, ny, nz. This is what we derived in the previous lectures. So, you have here sigma xx, sigma yy and sigma zz, tau xy, tau xz, tau yz, and this is symmetric. Now, the same expression we can use to identify the principal plane. How? Please pay attention. What is the definition of principal plane? So, principal plane is the plane where shear stress is 0. So, if we write down the stress field, 3D stress field along the principal plane, what will be the 3D stress field? We will have sigma along 3 orthogonal directions and there will be no shear stress. So, all the off diagonal terms will be 0. So, if we start from this 3D stress field where we have 3 components along 3 orthogonal directions, we do not know their magnitude, that we will find out. So, if we start with this stress field, then we can still find out the tractions along x, y, z using the same expression, because that will be equal to sigma, 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 that is the stress field, and then the direction cosine of the plane remains same, n x, n y, n z. Now, if we combine this expression, you can see this equation. So, from this we can find out the unknown, in this case is sigma. So, if we write down that equation in a slightly different form. So, what we have sigma x x, we take this matrix times this direction cosine on the left hand side and write a compact form. So, we have sigma y y minus sigma, then sigma z z minus sigma, then we have tau x y, tau x z, tau y z. So, this is symmetric, and then we have n x, n y, n z is equal to right. You can identify this equation. So, this is a eigenvalue problem. Now, we have this equation to solve, and the output of this equation is sigma, and also corresponding direction cosines what we have here. So, one of the solution you can easily conclude is n x equal to n y equal to n z is equal to 0. But that is a trivial solution that we are not looking at. So, this is a trivial solution, and obviously, we are not looking at this solution, right. So, we are looking at the plane where n x, n y, n z, they are not equal to 0. Obviously, for non-trivial solution, so this third bracketed term we can see here. So, this third bracketed term, if we take the inverse of that, that inverse should not exist, right. So, for non-trivial solution, inverse does not exist. Now, if you satisfy this condition, what is the outcome? Obviously, the determinant of this matrix is 0. So, we have sigma x x minus sigma, then tau x y, sigma y y minus sigma, tau x z, tau y z, then sigma z z minus sigma. Determinant of this matrix is equal to 0. We will solve this equation in a minute, but for principal plane, what is the conclusion? The first conclusion is we start with this 3D stress field. For the principal plane, we have to solve the eigenvalues of this 3D stress field. and for the principal plane, inverse of this matrix does not exist. Therefore, determinant of this matrix must be equal to 0. Okay, so, let us further solve this expression. So, we have sigma xx minus sigma yy minus sigma and then sigma zz minus sigma, and we have tau xy, tau xz, tau yz symmetric is equal to 0. Now, if you find out this determinant, you will get sigma cube minus sigma xx plus sigma yy plus sigma zz times sigma square plus sigma xx sigma yy plus sigma yy sigma zz plus sigma zz sigma xx, then minus tau xy square minus tau xz square minus tau yz square times sigma minus sigma xx sigma yy sigma zz plus 2 times tau xy tau yz tau xz minus sigma xx tau yz square minus sigma yy tau xz square minus sigma zz tau xy square is equal to 0. So, this is a cubic equation, you can see, and I leave it as a home task. Try this at your end. So, you have to expand this determinant of the matrix, and then you will get this expression. Now, we can write this expression in a compact form. We have sigma cube minus I1 sigma square plus I2 sigma minus I3 is equal to 0. So, that is the cubic equation in the compact form. So, what is I1? I1 is equal to sigma xx plus sigma yy plus sigma zz. I2 is equal to, you can identify this bracketed term. If I write it in a more compact form, it will be sigma xx tau xy sigma yy plus sigma yy tau yz sigma zz plus sigma xx sigma zz tau xz. And then finally, I3 is equal to the determinant of the 3D stress field itself. So, we have sigma xx tau xy tau xz sigma yy tau yz sigma zz. Okay. Now, please look at this expressions. So, we have I1 I2 and I3 that we get from the 3D stress field itself. The moment we define the 3D stress field, we can calculate these 3 quantities I1, I2, I3. So, these are called stress invariants. So, stress invariants are basically I1, I2 and I3. And then once we evaluate these 3 quantities, we can put it back in this expression, which is a cubic equation, and once we solve this cubic equation, then the solution of the cubic equation provides three roots, and these are sigma 1, sigma 2, sigma 3. These 3 roots are the solution of this cubic equation here we have derived, and these 3 roots are the principal stresses. Okay. So, we start from the 3D stress field, and then if we do the eigen analysis of the 3D stress field, what we get? We basically get the 3 roots of the stress field that we defined at the beginning, and these are the 3 principal stresses. Now, for each of them, so if we consider say sigma 1, then we can put it back to the previous equation. So, if you look at this equation, where in place of sigma, we can now put the value of sigma say 1, 1, 1, and then corresponding to this sigma 1, we can find out the direction cosines. But there is a small trick, because if you try to solve this equation, you will again end up with nx, ny, nz equal to 0. So, what we do? We consider 2 equations from this expression. So, say first 2 equations, you can take any 2, and then we also know there is a property of direction cosines. So, that is nx square plus ny square plus nz square, this is equal to 1. So, this is the third equation, and if we consider this equation along with the 2 equations from the original eigenvalue problem, then we can solve nx, ny, nz corresponding to sigma 1. So, that is the direction cosine corresponding to first principal stress. So, let us mark it say nx 1, ny 1 and nz 1. Now, similarly, we can also find out nx 2, ny 2, nz 2 corresponding to sigma 2, and nx 3, ny 3 and nz 3 corresponding to sigma 3. So, what we get is the principal stress and along with its direction cosines, because we have to identify the plane over which this normal stress acts, and on that plane there will be no shear stress. Okay. So, that gives us the 3 principal stresses sigma 1, sigma 2, sigma 3. We will solve some problem, and then we will see how we exactly derive these numbers from a given 3D stress field. That will solve maybe in the next class. But for the time being, what is more important is that this principal planes are orthogonal. So, let us quickly check that. Now, if we have a 3D stress field that is given, then from there we can find out sigma 1, sigma 2, sigma 3. Now, for each of them we have direction cosines. Just now we have discussed how to solve it. So, we have nx1, ny1 and z1, then nx2, ny2 and z2, and then finally, for third principal stress we have nx3, ny3 and z3. Okay. So, let we define the first principal direction n1 be nx1, ny1 and z1, and n2 second principal direction is nx2, ny2 and nz2. Okay. Now, we have two principal stresses sigma 1, sigma 2, and we have two principal directions. Obviously, if I take sigma 1 n1 dot n2, this must be equal to sigma 2 n2 dot n1, right. So, if we write down the expression here, so we have sigma 1, if I expand them, these two, what we have? We have n x1 n x2 plus n y1 n y2 plus n z1 n z2 is equal to sigma 2, and we will have the same quantity n x2 times n x1 plus n y2 times n y1 plus n z2 times n z1. Now, if we bring all of them on the left hand side, so this quantity if we take the other side and we have this first bracketed term common. So, we have sigma 1 minus sigma 2 times we have within bracket n x1 n x2 plus n y1 n y2 plus n z1 n z2, this is equal to 0. Obviously, in this case we have sigma 1 not equal to sigma 2, because we have three distinct roots, okay, three distinct roots. That means, sigma 1 not equal to sigma 2, obviously not equal to sigma 3, but for the time being we are not considering the third direction. So, for this condition, then if we use in this expression what we have here, what we get is n x1 times n x2 plus n y1 times n y2 plus n z1 times n z2, this is equal to 0. That means, n1 is orthogonal to n2. So, that is proved. So, we have two principal planes sigma 1 and sigma 2, with corresponding direction cosines n1 and n2, they are orthogonal. Similarly, we can also prove n2 is orthogonal to n3 and n3 is orthogonal to n1. That means, we have three principal directions, each of them are orthogonal to each other. Here I will just leave a home task for you. Prove that three roots of a 3D stress field are real and distinct. This we have already assumed here while deriving this, but you take this problem, just try it. So, what you have to do? You have to start with this expression here, and then you can prove that three roots of these equations for a 3D stress field is real and distinct. You try that. So, if you have any difficulty, then we will help you out. So, if I just sum up, what we have learned today is that if we start with a 3D stress field, what we have here sigma ij. So, this stress field once given, we can find out three stress invariants I1, I2, I3, and then if we do the eigen analysis, we get three principal stresses, and for each principal stress we can find out principal directions n1, n2, n3. I have discussed how to solve it. We have to use two equations from the original eigen equation and one from the property of this direction cosines, that forms three equations. We have three unknowns, so we can find out these directions. So, that completes the solution for the principal problem, principal stress for a given 3D stress field. You go through this derivation, and we have also proved that this principal directions are orthogonal. So, in the next class what we will do, we will solve some problem and we will see how to get this in terms of some numerical figures. If you have any doubt, please drop an email and we will try to clear your doubt. Thank you very much.